these are notes for Unit 6, Day 5, and you start on page 14 of your packet. And we're going to talk about something called the fundamental theorem of calculus and how it relates to accumulation functions. So if you remember, an accumulation function is where we start with a rate of change function, and that rate of change is graphed, and then we look at the area between that rate of change and the horizontal axis, and we accumulate that region, that area, and we know that that recovers information about the original function for us. So we're going to look at what the connection is. Our essential question then is, what is the connection between the accumulation function and the integrand? So remember, the integrand is that rate of change function. So if we look at this scenario here, we start out with this question. It says, what is a function defined by an integral of accumulation? So if we think about it, if we have this expression, it's pretty close to a definite integral, although a definite integral has numbers top and bottom, and this is a variable up here. We know the integrand is right here, 2t. We know that's our rate of change. So we're going to accumulate between that rate of change and the horizontal axis. So we know 2t is a linear function with slope 2, and so we're going to graph it, and we're going to look at the region between this function and the horizontal axis. And because we have a variable up here, what that means is that we're going to start at 0, and we're going to, and we don't have to, but it just makes more sense geometrically to start at 0. And we're going to accumulate out farther and farther and farther. That's what this table is saying. This table of x values is what are we going to put up here. Okay, so let's start off with the first value in the table. We're going to put a 0 up here. So we want to accumulate from 0 to 0 underneath this function 2t, and we want to know what the area is going to be. So if you think about it, if we start at 0 and we end at 0, then we haven't swept out any area at all. So the value's got to be 0 here. Now, before we go on, I want to kind of talk about this, because this is actually a pretty important property. So what they're saying is that if we don't sweep out, if we don't sweep across the horizontal axis at all, we're not going to have any area. We're not going to have any two-dimensional shape to calculate the area of. So hopefully intuitively that kind of makes sense. It certainly makes sense on this graph at 0, because we haven't even gotten into the shape yet, right? But we could put any value here as long as it's the same top and bottom. Like if we wanted to go put a value of 3 in here, and we wanted to go from 3 to 3, that means we'd start here at 3, we'd end here at 3, we still wouldn't sweep out any area. That value would still, then that accumulation would still be 0. So we've got our first accumulation value at 0. Well, now we want to go from 0 to 1. So we're going to sweep from 0 to 1, which means we're going to sweep out to 1, and then we're going to trap this region between the function and the horizontal axis. Okay, and we could recognize that as a geometric shape. So we're going to go ahead and use geometry. It's going to be half base times height, base of 1, height of 2. So that region has an area of 1. So our next accumulation value is 1. And so we're going to look at these accumulation values that we get, and we're going to try to define a function. So in other words, we want to find this. And this is going to be whatever comes of the pattern that we see when we start accumulating those areas. So let's accumulate out to 2 now. So we're going to go from 0 to 2, which means starting at 0, 1, 2. Again, we recognize that as a geometric shape. It's still a triangle. We have a width of 2, a height of 4, so that area is 4. So our next accumulation value is 4. Let's go up to 3 now. So if we go out from 0 to 3, we're going to have just a bigger triangle. Base of 3, height of 6, so that area is 9, and hopefully we're starting to see a pattern here. And then let's go out to 4. So if we sweep out to 4 here, we get just yet a bigger triangle, half base times height, half 4 times 8, and that is 16. So if we look at these values that we got as a result of our successive accumulations, basically, we look at this and can you see a pattern? So, you know, when we stopped at 0, we had 0. When we stopped at 1, we had an accumulation of 1. Stopped at 2, an accumulation of 4. Stopped at 3, accumulation of 9. Stopped at 4, accumulation of 16. So go ahead and stop the video for a moment and look at that and try to come up with a function that follows that pattern. Okay, if you're tuning back in, I'm guessing you've given that your best educated guess. So when we look at that, these numbers, we can generate these numbers directly by just squaring the x values, right? 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16. So this accumulation function then must be x squared. So looking at that and seeing that pattern allows us to actually get the function we started with, right? Just to go back to that whole idea of accumulation, we know that this is a rate of change, and excuse me, and when we accumulate under the rate of change, we recover that information about the original function. So the original function must be x squared. So we're going to kind of now use that as kind of a baseline and kind of make some general conclusions then from this pattern that we see. Before I leave this screen, though, I want to talk about. I'm reintroducing all of these triangles that we calculate the areas of, and I want to kind of introduce something here, just really superficially, that we're going to be delving into quite a bit during this unit, and that is the idea of like finding these individual regions. You know, the green triangle is hidden behind the red, and the orange triangle is hidden behind this stuff, and the blue triangle is hidden behind this stuff. And when that happens, the blue, the orange, and the green almost look like trapezoids because you're not seeing the tippy part of the triangle. So if we think about that, you know, how could we find the area of this orange trapezoid region? Well, we could accumulate from 2 to 3 and use a trapezoid equation. Or we could look at these values here, because we know that the orange triangle is 9 and the green triangle is 4, and realize that what's peeking out here is just the stuff that's left over. So this orange region must have a value of 5 just by subtracting these two values. So just kind of, you know, realize that we don't actually always have to start at 0. We can start anywhere and end anywhere and just capture the leftover or the stuff that's peeking out. Okay, just to kind of plant that seed. That's something we'll be delving into quite a bit in this unit. Okay, so moving on. So can you recognize the pattern above? And the answer was yes. We recognize the pattern above as an x squared pattern. So that makes g of x x squared. So as I accumulate underneath this linear function, I get an original function. This is the rate of change. The original function must be x squared. And so then the question is this: well, what if I took this result and differentiated it? What would I get? So what is the derivative of x squared? Pause the video maybe for a second and think about that. Okay, so welcome back. So that is what this is saying right here. They're saying, let's take the accumulation function right here and differentiate it. So take this and differentiate it, and you get 2x. So this is super powerful because look at what you get here and what you started with your accumulation function. They're basically the same thing with variable change. And so that is super cool because as long as we abide by this definition, and we're going to go over what this definition is later, we know that if we just differentiate the accumulation function, we get back what we started with. So that's kind of cool. So, and that's what the fundamental theorem of calculus says. Basically, we can accumulate, and then we can differentiate what we got, and we get back what we started with. We get back our rate of change with a variable change. And the reason why we have that variable change is, if you remember back on on the activity, we had a variable as the limit of integration. And so that allowed us to rewrite the accumulation function in terms of x instead of t. Okay, and so the idea is we're differentiating that accumulation function with respect to its new variable. So it's kind of like a do and undo thing. Start with the rate of change, I accumulate, and then I differentiate, and I get back what I started. So we know this is the rate of change, which is also the derivative. We know it recovers information about what we started with, which was x squared, right? We see the relationship between starting here, differentiating, and getting here. And so the definition then is we accumulate a rate of change. That's this definite integral part. We differentiate that result. We have a variable change here that's occurring as a result of that. And you get back what you started with that variable change. And so as long as we adhere to that definition, then really we don't even need to know what the original function is. We can just jump right from this to the result, putting in the variable change. So that is hugely powerful, because that allows us not to have to run through that whole accumulation step and find that pattern if all we're going to end up doing is differentiating it anyway. So let's see how this works. Okay, we're going to the first thing we're going to do is we're going to see how this works in terms of motion concepts, because you have a lot of practical experience with things like position and velocity, right? So we know the velocity is the rate of change of position with respect to time. So velocity is a rate of change, right? So that's our accumulation function. That's what we're going to accumulate underneath. And so we're going to accumulate from A to some location T, and hold off on, well, no, get this written down, and then we're going to kind of go over it. We're going to accumulate the rate of change. Now, notice the variables I'm using here. Because we're talking about motion, and motion is usually with respect to time, we have to end up with the variable of time at the end, so after the variable change. So our upper limit needs to be t, not x, because it makes more sense with motion questions, which means we can't use the variable t down here, because that would be introducing ambiguity. So I arbitrarily pick the variable. It really doesn't matter what variable, as long as this matches. So we have a velocity function in terms of u, and we're going to graph that, and we're going to accumulate the area between some starting numeric value a, this is a number, and some random location t. And that is going to be defined as our position, because we know that if this is the rate of change, when we accumulate area underneath it, we're going to recover information about what we started with. So if we differentiate position, which means differentiating this, we end up with our rate of change, our velocity with respect to time, with that variable change. So let's apply this. So we have our drone back. We have our altitude of our drone is given in feet, and the altitude is given by this accumulation function, right? We're accumulating the rate of change, where t is measured in seconds. So the question is, what is the rate of change in altitude when t is 4 seconds? That's the first question. What is the rate of change? So we're looking for the rate of change, the rate of change function. So we know our accumulation function is this. And if we want the rate of change, that means we need to differentiate the altitude function, which is the accumulation. So we need to differentiate this. Well, if we're differentiating our accumulation function, that means we're just getting back this function with the rate of change. So our rate of change over altitude is just 64 minus 12. That should be a t. I forgot to do the variable change. Okay, I am going to correct that. because that's too important not to correct. There we go, make it a T. There we go. Okay, let's get us back to where we were. There we go. Okay. So the rate of change of our altitude is 64 minus 12t. Now we have that variable change. Okay, so it's, what is the rate of change in altitude when t is 4 seconds? So we're going to plug 4 in here. So we're looking for h prime of 4. That's what that question is. What is rate of change of altitude when t is equal to 4? So plugging 4 into here and doing the math, we get a rate of change of 16 feet per second. I could have used the feet / seconds too, but I just did FPS. Okay, second question is, at what time does the drone change direction? So change in direction means that we have a rate of change of 0, right? If we're going to go up, change from going up to coming down, that means we're changing our velocity from positive to negative. And if we're going from positive to negative, we're going from 0. So we need our rate of change to 64 minus 12t. We're going to set that equal to 0 and solve for t. So bringing the one of those to the other side, maybe the 12t, dividing by 12, we get a time of 64/12 seconds. Don't need to reduce that if you don't want to. So that's kind of in the context of motion. That's how we would use this. So if we look at this, just to kind of look at the big picture here, because we're being asked for a rate of change in altitude, and we have altitude as an accumulation expression, we're basically just differentiating this. In other words, we're looking at this fundamental theorem of calculus as another differentiation rule, basically. And the nice thing is that it's just because it's an accumulation and differentiating it, you're just getting back what we started with. So accumulating and differentiating kind of undo each other, kind of like addition and subtraction, or multiplication and division. Those are, square rooting and squaring. We have these properties in math that undo what we just did to something, right? If we start at 4 and we add 7, we get 11, and then we subtract 7, we're back at 4, right? We have these things that do and undo, so to speak, in math. And this is another one of those concepts where we start with a rate of change, we accumulate, that's the first thing we do to it. We differentiate, which basically means we undo what we just did. We get this back with the variable change. So that is why we call it the derivative part of the fundamental theorem of calculus. Okay, let's talk about tangent lines, because we talk about writing tangent lines all the time, right? What do we need to write a tangent line? We need slope and we need a point. Okay, so if we need those two things, we already know our x-coordinate is -2. We got to find the slope, which means we need to find the derivative of this function. Well, in part, it's like an accumulation function. So we need to find f prime of x, which means we need to differentiate this. So we got two terms here. It's 3 is one of the terms, and this accumulation function is the other term. We need to differentiate each one of those terms. So we differentiate, the derivative of 3 is 0. The derivative of the accumulation just gets us this. Now this is where this is super duper powerful, because if we're differentiating an accumulation function, all we know we just get this with our variable change. Notice I'm starting at -2 because that's where it's telling me to start. Who wants to graph this and try to accumulate area underneath it and for pattern, and then just differentiate that pattern? We don't want to do that. And the nice thing is we don't have to, because all we're doing is being asked to differentiate this accumulation. And so we know we just get what we started with that variable change. Notice the x is there, the t is gone. Here's our derivative. So now we're going to evaluate that derivative at -2. So we're going to stick in -2 here. Squaring -2 gives us a +4. So we have sine of 4 pi over 8. Reducing this gets us pi over 2. So we have to I can get rid of the 0 at any time. So sine of pi over 2, think about the unit circle. Pi over 2 is at the top. Sine is the y coordinate, right? We're gonna do that. Blackboard quiz, second semester too. and keep those trig values sharp. Y coordinate is 1. So the derivative at -2, f prime of -2 is 1. So we know that's our slope. Okay, so we're halfway there. We've got our slope now. We need our point. We've got our x. We're going to find our y by coming back to the original function and sticking in -2 for y. Excuse me, -2 for x. Okay, so here's the original function. We're going to stick in -2. What that means is that this bound up here at the top becomes a -2. We talked about this, right? We talked about when we accumulate and we start and end at the same spot, we don't sweep through any area. So pause the video, think about that. What does it make this value then? Yeah, if you're back, I'm assuming you kind of paused it for a second or two to think about that. So if we don't sweep out any area because we're here at -2 and we stay at -2, then the accumulation between -2 and 2 must be 0. So this whole thing is 3 plus 0, which means my y coordinate is 3. So I know I'm at -2, 3. I've got a slope of 1. I got to put all that stuff in this. Remember, this is the front of the room. I think I even got the color coordination right. This is the front of the room. The anchor chart at the front of the room. Here's my slope points form of the equation. Far more convenient. I'm going to throw my slope in there. I'm going to throw my points in there. There's my tangent line. You don't need to clean it up at all. If you wanted to make this a plus, you could, but you don't have to. Okay. Sometimes they put the 3 over here and say y minus 3 equals. I don't like that. Sometimes con makes you do that. I like to solve for y because you're being asked for an equation for a line that should be y equals. Okay, so that's how we deal with tangent line concepts. We're still going back to those really fundamental things, right? Tangent lines, those sort of things, they're going to stay with us all year long. Okay, so when we get back into the classroom, we'll talk about the other kind of more complicated aspect of the fundamental theorem of calculus. And that would kind of require us to be a little more face-to-face so that you can ask questions along the way.